we take a look at our next problem? Well, in this question, we want to talk about class method and get an understanding for what is the design thinking behind class method. Class method is another one of these decorators that we see very commonly alongside property. We understand why it is that property may come up commonly. Where does class method come up commonly? Well, here's our first premise. We want to avoid churn. And when you look at some code like this, you might say, there's something somewhat dissatisfying about this code. I've got a bunch of functions that are operating on a data set. I load some data, I clean some data, I generate a report, I save some results. I've packaged them up in a run report function, and I'm calling that from my main. You might say, well, there's a lot of levels of indirection here. The main calls run report, which calls each one of those, which actually does the work. And one of your first intuitions is, I don't know how I feel about this global variable here. And that might be more of a knee-jerk reaction than something that is particularly principled, because at least here, the code works. It does exactly what it says, and I don't know that the global variable is the problem. What may be the problem is, if we need to change this code in some fashion, well, then we probably are changing the code at this level, because that's all where all the work is being done. And one of the things that we might think is the reason that we wrote these functions in the first place is because they're used in other places. It's not just this one run report function that uses load data. There may be many people who use this load data as part of this run report. It may not be the case that it's just this main that uses this run report. Otherwise, why wouldn't you just have written it like this? It may be the case that other people need to run this run report function. And so when you make changes to this innermost level, especially since it's so deeply nested, think about how for each deeper nesting of this code, for each library that you go closer to the standard library, the fan out of the number of places where this could affect or code churn is going to be quite significant. If you make a change at the main level, well, probably that's only ever used by you. So the changes are quite minor. If you make a change at the library level, well, it's every user of that library. If this is a consequence of there being a library with a more core more library, with a more core more library, a stacking of libraries, then you can think that the deeper you go into this hierarchy, the more of a fan out of changes that you have. Because, for example, a change of one line to the Python standard library has enormous consequences in the world. A change to one line for something that's built on top of the standard library, like a third-party library, has big changes, but not as enormous. As you go higher in this hierarchy, the churn amplifies. And if we were to try to improve this code, to try to remove this code churn, well, maybe one of the things that we might do is we might make it run on local variables. That addresses the global variable problem, but I don't know that that's really such a huge change. I think we still have the case where a one-line change here is going to have large consequences, and we just rewrote run report, and maybe at most we could actually return something from this, but we can always access from the global scope. I think the problem here is when you look at that code, what makes you uneasy is each one of these steps may be idiosyncratic or may have some ad hoc behavior associated with it. For example, clean data. Well, multiple people are using clean data. Do they all have a unique, singular view of what it means to clean this data? Do they all clean it in the same way? Or does somebody want to remove outliers from this data? They want to take the data and they want to remove any values that are greater than one standard deviation from the mean. So they want to take any values here. This is my temp. They want to say return this temp where the value is greater than one standard deviation from the resulting mean. And here, do they want to do the filtering first, or do they want to do the outlier removal first? That's another modality. That's another choice that somebody might make that might be different. And when we think, whenever we create a function, we're creating a single source of truth. If it's the case that that single source of truth isn't actually a single source of truth, people have different perspectives based on what this function should do. One of the consequences of this is we introduce code churn, and we introduce code churn by introducing additional keyword arguments. Here, we have some keyword argument. Somebody's going to say just add a flag. So we just add a flag here to include the removing outliers or not. So here, if we say if outliers, we return temp. Otherwise, we remove the outliers and return temp. But if somebody says, okay, but maybe we do outliers first, that's another flag. And then we have to rewrite this to take into account the two different ways we do this. And you can think that these things just grow and grow and grow. And because this is library code, every time we add a keyword argument here, we got to check, or at least have some certainty that we didn't break somebody else's code. This is why people say add a flag with a default value, because that's their way of saying, well, probably adding a flag with that default value has no consequence, because in the cases where nobody knew that this existed because their code used this prior to the change, well, they're just going to take the default behavior and there should be no change. But one of the things you can think is every time you change this library code, you have to have some guarantee that you didn't break something somebody did. You have to do some revalidation, either by saying it's a flag, everybody's just going to take the default behavior, or by performing some actual testing. In fact, my argument historically has been that this is the best way to write this code, because each step of this, where we load the data from, how we perform the data cleaning, how we generate the report, how we write the results, might diverge over time from somebody's single source of truth, and we want to preserve the ability to make these changes without the disruption of churn. And I want you to consider what happens when we have this churn. It's not just revalidation, but it's also related to the timing of this disruption. Think about this. In the first version, we presumed that the data was going to be written out to just a plain text file. But what if the data is going to be written out to an email or to a database or to some sort of formatted text file, and somebody needs to make that change? And in the very first version, you'd have to add all of these flags, save the results as plain text, and maybe that's set to true. But the other option is to database, and that's set to false. And then you have to make these changes here and make sure that nobody's code, or have some guarantee that nobody's code changed there. And that change may occur deep in your code when you least expect it. Somebody might say, oh, I want you to make a small change to this report, how you write the data out or how you format this. I want you to capitalize mean and write out standard deviation. And they ask you to do that at 5 p.m. on a Friday. And you think, ooh, do I really want to release a change to this code at 5 p.m. on a Friday with just a very casual revalidation by saying, probably nobody else's code changed, and then discover that everything breaks over the weekend and you have to come in on the weekend? No. The timing of this churn is a key criteria. And what you can think is, by superficializing all of this behavior, making it so that it's not in a function but in your if name equals main block, well, you've significantly reduced the place where this churn could then cause revalidation. Another thing I want you to consider is, one of the consequences of writing functions and designing your code in this particular fashion is, when you add flags, when you see this churn is not only adding some disruption for revalidation, and is not only possibly happening when you don't want it to happen, but it's also introducing geometric complexity, because as you add flags, you increase the number of possible code paths. And even if these code paths were exclusive, even if it were the case that you set flag 1, flag 2, and my newly added flag 3, they're exclusive, only one of them can be set. In your test, you probably have to take into account, for coverage reasons, that you need to test every possible geometric combination of these. You need to test the geometric expansion of these. You need to test the Cartesian product of all the possibilities of flag 1, flag 2, and flag 3. And the reason for that is, yes, you might be able to say that they are exclusive today, but you need this test to make sure that somebody tomorrow doesn't accidentally make these non-exclusive, causing another error. And so you actually need to add another set of tests every time you add one of these flags that are not necessarily related to just the flag that you added, but the combination of that flag with every other possible code path. In other words, you see a geometric expansion of the number of tests you have to write. Every time you add a flag, you need to double the number of tests to take into account the doubling of the number of possible code paths if it's just a true or false flag. Here's another premise. When we see this churn, it is oftentimes localized. It's oftentimes a consequence of any interaction with the outside world, especially the churn that happens when we least want it to happen, when we least expect it. When we're dealing with churn as a consequence of something that's deep in the insides of something we control, in the insides of our library itself, well, usually we can say, you know what, I'm not going to make that change to the library. I'm going to schedule that for the next iteration of the library. I'm going to schedule that for the next breaking change. But if the churn is a consequence, or if the change is a consequence of something in the outside world, you may not have the ability to decide when you want to address it. If your data format changes, you can't say, oh, I'll wait till the next version. You have to fix that data feed right then and there. Churn is oftentimes very much localized, very much a consequence of changes to input and output data formats, things that affect the outside world. Things like input data cleaning, things like output data projections, like your aggregations, your filtering, your visual formatting. It's often the case that when that churn happens, somebody says, you know what? I need you to make a change to the report. And can you make it in the next 15 minutes? And it's also 5 p.m. on a Friday before a 3-day weekend. And I need you to make a very small minor change. Well, you can see that that is the worst kind of churn because you're under time pressure. It's not something that you anticipated doing. You were already packing up to leave for the day. And if that requires significant revalidation, you just ruined your weekend. What we'll see in a piece of code like the one that we saw was any time we read from some input data source, we write to some output data source, we have a potential source of churn. We have a potential source of somebody coming to us and requiring that we make a change to this, which then requires changes to our testing, which may require a geometric expansion of the number of tests we have, that may require revalidation. So it is very, very, very high risk for our sanity, for our control over our own time. As a consequence, we have to be very careful around whether we put data loading or data saving, anything that works with the outside world, deep into our code bases because it's a source of churn, which is going to be a source of disruption in our work. Here's another premise. The data loading may require close cooperation with types representing the data. So, generally, my guidance is don't write your code like this. Write your code with anything that interacts with the outside world as superficial as possible so that you can make immediate targeted changes, change the way the report is written, change the name of the file, change the format of the file, and you can make those minimizing the amount of disruption and the amount of churn. You can make those very quickly. But the problem is the data loading may be closely associated in space to the underlying types that represent that data. In other words, this class T may really be the source of truth, the source of knowledge for how the data cleaning may occur. And so you can't necessarily superficialize that data cleaning so easily. It may be the case where that data cleaning needs to happen very, very close in time to the construction of this type and very close in space. The code that's involved in this data cleaning needs to be located around the same space where the code that does things with these type changes, because you can think that if it were the case that we change this from a square loop to a log operation, then we really want the data cleaning to be really close by so that we know, oh, you know what, the domain error for the log is different than the domain error for the absolute value. We can't compute the log of, any value that's, say, less than 1. And so, as a consequence, or whatever the mathematical function may be, here's another premise. The computations that we perform are generally parameterized on data and metadata. I want to introduce to you the idea of modalities whenever we're performing some computation. And whenever we are trying to parameterize that computation, we parameterize it in 2 ways. If you see a function called f that's written like this that takes no arguments, you can probably guess what this f does. This f either performs some action where the consequences are the outside world, otherwise why wouldn't you pass in any arguments here or return anything? Or this f relies on some hidden state and maybe returns something or performs some operation on this hidden state. And bear in mind there's a very loose distinction between this, which performs an action, and maybe this, which returns something that performs some computation. Or maybe this code here performs some operation on dependent state, so there's a timing situation. But whatever the case may be, whenever you see a function that doesn't take any arguments, you kind of have a good sense for why that function doesn't need arguments. Usually, it's performing an action, which is not parameterized in any fashion. It's working on some hidden state, so it's parameterized but not in a way that you can visually see. Or it's just a timing issue. It's something that you could have done not as a function, but you needed to delay the timing of it, and so this is just a timing indirection. You often see this with things like a binding, or you see this in cases where you pass a string and then you resolve that string to the underlying type. But when you see a function that takes arguments, well, you can usually split those arguments into 2 general classes. Arguments that are the data, the thing which the function is operating on, and arguments that are the mode, the modality, how we go about performing that operation. Here, it's very clear. The data that we operate on is some numeric value that we're either squaring or cubing, and the mode tells us how we go about doing that operation. It's often the case that when we pass in modalities, we pass them in as keyword arguments. And the reason for that is if you think about something like pandas.readcsv, do you ever pass file name equals to pandas.readcsv? No. Read CSV obviously works on something that's either a file object or a file name. You don't need to pass that as a keyword argument. Now, if you happen to have a non-standard separator, when you call read CSV, do you just pass that separator as a second argument? No, because nobody could tell what on earth that means. What does that pipe all by itself mean? But if you write read CSV, data.csv, separator equals pipe, oh, everybody knows, oh yeah, well, obviously you're operating on some CSV data in this file name, and the modality with which you go about operating on this, the modality for how you separate each one of these fields is with the pipe. Well, you can see it is very common that our data parameters are passed positionally, and it is extremely common, so significantly more so than, because you can sometimes pass data parameters by keyword, and it sometimes makes sense, but it's significantly more so the case that you want to pass those modal parameters as keyword arguments. One interesting side thing is, when you think about a generator, you think about a generator as repeatedly returning some incremental result. When you think about a coroutine, you think about it as returning some incremental result, but also taking incremental data. Here, and you think about the coroutine as it can take data in two ways. It can take its parameters, it can take its inputs in two ways, either when you construct the coroutine instance or when you send data back into it. But another very interesting pattern that you might see is it's often the case that when you write a coroutine, the modal parameters are what you pass to instantiate the coroutine instance, and the data parameters are the ones that you pass in via send. Now, that we're talking about modalities, I want to talk a little bit about bounded versus unbounded modalities. When we see the modalities on a function, it's often the case that we can identify whether this is a bounded or an unbounded modality. And this is a very loose designation. Here's what I mean by bounded. If we have a load data function and it takes a source and it's prod or dev, this is bounded. There's only two possible options. But if it also takes a timeout action, that's unbounded. What is that timeout? 1 second, 1.1 second, 1.1 second, 1.11 seconds. The possible values for this have some unboundedness. But that's not really true because this timeout is a floating point value, and Python floating point values are IEEE 754 double precision floating points. So there's only 2 raised to the 64th power. There's only 2, shall we say, 1,000, million, billion, trillion, quadrillion, quintillion. There's only 18 quintillion possible options, but there are finite. It's a bounded set of 18 possible quintillion, 18 quintillion possible options. Well, bounded is usually a very loose designation. We usually say that bounded means a small number of human tractable possible options, and unbounded means either intractable to human being or literally infinite. Because if this were, for example, a Python int, well, there's no maximum size to a Python int. It's only bounded by how much memory you have, and so you could say this is actually genuinely unbounded because the only bound there is the amount of memory you have, and memory is effectively unbounded. What this leads to is the key premise. When we have independent bounded modalities, we can do a nominal decomposition on them. In other words, if I have this function and it has a modal parameter, a true or a false parameter, I can write it like this, where it has this parameter, and under one mode it does a square, and under the other mode it does a cube, and by default it does the square. And I can even take in that modality as some user input and then pass it through to this function. Or, because this parameter is bounded, because it is limited to a finite, small, human tractable set of options, I can decompose these into independently named entities where each name represents whether the parameter is set to true or false. I can take that exact same code and I can write fmode and fnomode that decompose this code into 2 separate functions. It actually also linearizes this code, and when I want the f with the mode version, I can say fmode. When I want the f without the mode version, I can say fnomode. The default's a little bit harder for me to deal with. I probably need to have one more name representing the default value, and passing in user input is a little bit clumsier to do, but it's still possible. I can just choose at runtime, based off of user input, which of these 2 functions I want to call, as opposed to passing that parameter in. One thing that's interesting about this decomposition is it linearizes complexity, because in the case where I'm adding flags and flags and flags, if these are bounded modalities, well, if I'm adding them over and over and over, we know that I'm geometrically increasing. I'm doubling the number of tests I have to write. I'm doubling the number of possible code paths. But if I add in modalities by just writing a brand new function, then I'm just adding one piece here and one test here, and that's it. In other words, the growth in the complexity of my code is no longer quadratic, or it's no longer related to the Cartesian product of all of these modes, it's now just linear. One more mode, one more function, one more test. Here is our conclusion. As related to class methods, we oftentimes want to nominally decompose modalities associated with data loading. Here's what I mean. If we have a class that takes some data, and it takes that data by reading it from some external source, it interacts with the outside world. We might write this class in its initializer to take a file name and then read from this file name until somebody comes to us and causes churn. Because this is probably library code, that churn has enormous consequences on anybody who uses this class. And if they say, oh, just add a JSON equals false flag, and under certain circumstances make the data JSON, and other circumstances make it plain text, well, it's an easy enough code change, but then I have to revalidate all the places where this code might be used, which might be enormous. And I have to go to my tests and I have to update my tests. And this can be very disruptive to my work. One of the problems is this disruption can also happen when I least expect it or when I want it to least happen. But note that as people add these parameters here, oh no, not just JSON data, also deal with pickle data, and this grows and grows in complexity, these are fundamentally bounded modalities. It's either reading from plain text or reading from JSON data or reading from pickle data, which means I could decompose this nightmare of an init where people have just added keyword argument after keyword argument. Here they've even added a keyword argument where they want to deal with the JSON key. Like maybe the JSON data is a couple of keys down. So they want to deal with going down some particular path. Well, I could decompose this into separated functions. And some initializer for the plain data, some initializer for JSON data, some initializer for the pickle data. This is a nominal decomposition of a bounded modality. There's only fixed modalities here. You're either JSON mode or plain mode or pickle mode, and you can decompose it. And you notice the code is a lot easier to test because you don't have that complexity of those code paths. And there are certain modalities, like this unbounded modality, that we might package together. It's not like we can say init JSON with key A, key B, key C. It's an unbounded modality. Consider that one of the consequences here of having data model methods is they must be unique, they must be unambiguous and privileged. So I can't actually write my code like this. I can't have 3 initializers. This isn't C++ after all. So what I'm actually forced to do is to have 3 separated methods. But the problem is now it's separated the methods from the type, and we said one of our core premises is that it's often the case that the type needs to know how the data was loaded in order to do adequate data cleaning or the computation of dependent parts. Here, our init is basically the dumbest init we can have. It just takes some raw data and sets that raw data, but we've lost our grouping. Well, this is exactly what class method is. Class method is a common pattern for us to take a modality that we see in our code, a bounded modality, typically related to the mechanisms by which we instantiate some data, that allows us to keep that instantiation, that input data, that loading of data very close in space to the underlying class, and to linearize the complexity here as opposed to having some init that becomes more and more and more complicated. Because when somebody comes and they say, well, you know what, I also want you to write a loader from XML, you just write another class method. And here's the great thing about writing this other class method. Your revalidation is very minimal, because you know that if nobody ever called this function, there could be no problem. And so because you're not changing any one of these, there's really no risk. The revalidation is quite simple, and the test for this is very simple. You just have to deal with that one consideration. When you think about class method, I want you to think about it being over 80% of the time about implementing factory functions to instantiate types, because it is one of these patterns that we have, decomposition of bounded modalities, whose goal is to eliminate churn, because we know churn oftentimes comes up when we're dealing with the outside world, namely dealing with data loading or data saving. And it is often the case that we can't completely superficialize that because the data loading really does have some need to be very close to the underlying type that it's loading the data into.